124 light-years away, hidden in the vast darkness of space. Scientists have just found something extraordinary. A planet, nearly 8 times heavier than Earth, has given us the strongest evidence yet that we may not be alone in the universe. The James Webb Space Telescope has detected certain molecules in its atmosphere, molecules that, here on Earth, are only produced by living organisms. Among them is dimethyl sulfide, a substance created on our planet only by marine life. Alongside it, scientists also detected specific patterns of methane and the presence of water vapor. Together, these signals look remarkably similar to the chemistry of life as we know it. This is no longer just speculation. Researchers now estimate there is a 99.7% chance that some form of biological process is happening right now on this distant ocean-covered world. Subscribe and stay with us as we explore what may be the most important discovery in human history. Get ready. This is just the beginning. When the first images and data appeared on the computer screen, astronomer Niku Madusan could hardly believe his eyes. The screen lit up with colorful lines of spectral data, and he whispered one word: impossible. What he was looking at simply should not exist. The James Webb Space Telescope had captured chemical signals from a planet so far away that its light has been traveling toward us since long before humans ever invented writing. Yet within those infrared readings were unmistakable molecules that seemed to spell out the presence of life. To give you an idea of the challenge, it's like trying to detect a single drop of perfume in a swimming pool from 3 miles away. And yet, Webb managed to do just that, identifying tiny traces of molecules in the atmosphere of a planet called K218b, 124 light-years from Earth. Every wavelength of light coming back from that planet revealed information about the gases floating in its skies, and the story they told left scientists breathless. The data showed dimethyl sulfide in those faraway clouds. Here on Earth, this compound has only one source: life itself. Tiny ocean organisms release it into our air every single day. It's a chemical marker of biological activity as clear as a fingerprint. But that wasn't the only discovery. Methane and carbon dioxide were found in exact proportions that resemble the early atmosphere of Earth, at a time when our own planet was full of primitive life. On top of that, water vapor appeared in the readings, hinting at the possibility of vast oceans lying beneath thick hydrogen-rich clouds. Shaken by what he was seeing, Madusan called a colleague at Cambridge University. "You need to see this immediately," he said, his voice filled with the excitement of someone realizing history was unfolding before their eyes. "We're looking at an atmosphere that cannot be explained by natural chemistry alone. There's only one explanation left: life." The calculations kept confirming it. Every test pointed in the same direction: biological activity. Right now, as you hear this, the air on that planet contains the exact mixture of gases that you would expect from a living, ocean-based ecosystem. For decades, scientists have searched the skies for signs of life. They've found frozen water on Mars, organic material on asteroids, and distant planets that seemed potentially habitable. But never before have they discovered something like this: clear, ongoing signs of biological activity streaming across space like a signal waiting to be read. And now, for the first time, humanity stands at the edge of answering the oldest question of all: are we alone? The Discovery team ran the analysis 17 different ways. Every mathematical model, every chemical simulation, every atmospheric physics calculation pointed to the same stunning conclusion. Something alive was breathing, eating, reproducing, and dying in the skies of planet K218b. What made this discovery even more remarkable was that it almost didn't happen. James Webb had been pointed at this particular world to study its basic atmospheric composition, not to search for life. The biosignatures appeared as an unexpected bonus, a cosmic gift wrapped in starlight and delivered across the vast emptiness of space. Yet this was only the beginning of the story that would rewrite every textbook on astrobiology. Within hours of the discovery announcement, every major observatory on Earth was scrambling to point their instruments toward the constellation Leo. K218b had transformed from an obscure catalog entry into the most important celestial object in human history. Astronomers who had spent their careers studying distant galaxies suddenly found themselves canceling observations to focus on this single point of light floating in the cosmic dark. Conference calls erupted across continents as scientific teams coordinated the largest collaborative observation campaign ever attempted. What made this world so special wasn't just the potential for life, it was the perfect combination of factors that made detection possible. Think of it like finding a needle in a haystack, except the haystack is the size of the entire universe, and the needle is glowing with exactly the right color of light. K218b orbits its star in a way that creates what astronomers call a transit. Every 73 Earth days, the planet passes directly between its star and our telescopes, blocking a tiny fraction of starlight. During these cosmic eclipses, some starlight filters through the planet's atmosphere before reaching our instruments. That filtered light carries the chemical fingerprints of whatever gases float in those alien skies. The discovery triggered a gold rush mentality in the astronomical community. Research teams that had been working on completely different projects suddenly pivoted their entire focus to this single world. Graduate students found themselves reassigned to analyze atmospheric data instead of studying black holes or galaxy formation. Postdoc researchers who had never worked on exoplanets before were crash coursing in atmospheric chemistry. Space agencies began fast-tracking missions that had been sitting in proposal stages for years. The European Space Agency dusted off plans for next-generation space telescopes specifically designed to study potentially habitable worlds. Private companies started calculating the cost of sending robotic probes on 100-year journeys to actually visit this distant ocean. But the most dramatic change happened in the funding world. Astrobiology programs that had struggled for decades to secure adequate resources suddenly found themselves drowning in research grants. Universities competed to hire specialists in atmospheric spectroscopy and exoplanetary science. The search for extraterrestrial life, once considered a fringe scientific pursuit, became the hottest field in astronomy overnight. Social media exploded with speculation and excitement. The hashtag Kiwa218b trended globally as millions of people shared their thoughts about humanity's potential cosmic neighbors. Science museums prepared new exhibits almost instantaneously. Planetarium shows were rewritten to feature this remarkable world. Religious leaders grappled with theological implications, while philosophers debated what the discovery meant for human uniqueness in the universe. Science fiction writers found themselves struggling to imagine scenarios more exciting than reality itself. The planet had become more than just a scientific curiosity. It represented the answer to one of humanity's oldest questions. Are we alone? For the first time in human history, the data was pointing toward a resounding no. Yet beneath all the excitement lay a sobering reality that few people were discussing publicly. Dimethyl sulfide smells like rotting cabbage mixed with ocean water, but it might just be the most important molecule in the universe. This simple chemical compound consists of just 5 atoms, one sulfur surrounded by 2 carbon atoms, each bonded to 3 hydrogen atoms. On Earth, every single molecule of dimethyl sulfide in our atmosphere comes from the same source, living organisms. There is no known geological process, no chemical reaction, no natural phenomenon that can create this molecule without biology. Picture the most remote ocean on our planet, thousands of miles from any land. Even there, microscopic phytoplankton are constantly pumping dimethyl sulfide into the atmosphere as they go about their daily business of photosynthesis and reproduction. These tiny marine organisms produce approximately 20 million tons of this chemical every single year, making it the primary source of sulfur in Earth's air. The molecule plays a crucial role in cloud formation over our oceans. When dimethyl sulfide rises into the atmosphere, it undergoes chemical reactions that create particles around which water vapor can condense. These particles become the seeds of clouds that help regulate our planet's temperature and weather patterns. In essence, microscopic life forms are actively participating in Earth's climate system. Scientists have searched extensively for non-biological ways to produce dimethyl sulfide. They have subjected various minerals to extreme temperatures and pressures. They have simulated lightning strikes, volcanic eruptions, and asteroid impacts. They have tested every conceivable chemical reaction that might occur naturally on a rocky planet. The result has always been the same: no dimethyl sulfide without life. This makes the molecule what scientists call a biosignature, a chemical that reliably indicates biological activity. Unlike other potential signs of life that could have geological explanations, dimethyl sulfide is unambiguous. Its presence in any planetary atmosphere would be like finding a note written in a language that only living things can speak. The detection of this molecule in the atmosphere of K218b sent shockwaves through the scientific community, precisely because of its biological exclusivity. When James Webb Space Telescope identified the spectral signature of dimethyl sulfide in those distant clouds, it was essentially detecting the waste products of alien metabolism floating in space. But here's where the discovery becomes even more remarkable. The concentration of dimethyl sulfide detected around K218b is actually higher than what we typically measure in Earth's atmosphere. This suggests that whatever organisms are producing it on that distant world are either more abundant or more active than the phytoplankton in our own oceans. The implications stagger the imagination. We're not just looking at evidence of life, we're potentially looking at evidence of thriving, abundant life, an entire ecosystem of microscopic organisms breathing, eating, reproducing, and releasing their chemical waste products into an alien sky 124 light-years away. The molecule had revealed its secrets across the vast emptiness of space, carrying a message that took 124 years to reach our telescopes. But the message it delivered was worth the wait. Something was alive out there, and it was talking to us in the universal language of chemistry. Mathematics doesn't lie, and the numbers streaming back from K218b were telling an incredible story. Scientists don't just look at atmospheric data and guess whether life might exist. They use sophisticated mathematical models that calculate probabilities based on thousands of different variables. Think of it like a cosmic crime scene investigation, where every molecule is a piece of evidence that either supports or contradicts the hypothesis of biological activity. The calculation begins with something called the chemical disequilibrium principle. On a lifeless world, atmospheric chemistry tends toward a state of balance, where all possible chemical reactions have reached completion. Oxygen reacts with methane until one or both are consumed. Carbon dioxide dissolves into any available water. Over millions of years, the atmosphere settles into a stable, predictable pattern. Life throws this balance completely out of whack. Living organisms constantly pump gases into the atmosphere that shouldn't coexist under normal chemical conditions. They produce oxygen and methane simultaneously. Even though these gases react with each other, they maintain carbon dioxide levels that differ dramatically from what geology alone would predict. When scientists analyze an exoplanet's atmosphere, they first calculate what the chemistry should look like if only geological processes were involved. Then they compare this baseline to the actual observations. The bigger the difference between predicted and observed chemistry, the higher the probability that biological processes are interfering with natural atmospheric evolution. The atmosphere of K218b showed chemical signatures that were wildly out of equilibrium. Methane coexisted with water vapor in concentrations that defied purely geological explanations. Carbon dioxide levels fluctuated in patterns that suggested active removal and replenishment. The presence of dimethyl sulfide added another layer of chemical impossibility to the mix. Researchers ran computer simulations, modeling every conceivable non-biological process that might explain the observations. They tested scenarios involving volcanic activity, lightning strikes, meteor impacts, and exotic atmospheric chemistry. They pushed the models to their absolute limits, looking for any possible way that geology alone could account for what James Webb was detecting. The results were definitive. The probability that purely geological processes could produce the observed atmospheric chemistry was less than 0.3%. This meant there was a 99.7% chance that biological activity was responsible for the chemical signatures. But the calculation didn't stop there. Scientists also had to consider the possibility of instrumental error or misinterpretation of the data. They reanalyzed the spectral information using multiple independent methods. They compared results from different instruments on James Webb Space Telescope. They invited rival research teams to examine the data and attempt to find alternative explanations. Every analysis confirmed the same conclusion. The chemical evidence for life was overwhelming, unprecedented, and mathematically undeniable. The probability calculations had crossed the threshold that scientists use to claim a discovery. The same statistical standard applied to everything from particle physics to climate science. These weren't wild speculations or hopeful interpretations. They were cold, hard numbers generated by rigorous mathematical analysis of empirical observations. The universe had presented humanity with an equation, and the solution was life. Yet, probability isn't certainty, and the most important questions still lay ahead in the data that remain to be analyzed. Sometimes the universe aligns in ways that seem almost too perfect to be accidental, and K218b represents one of those cosmic coincidences. This world sits in what astronomers call the Goldilocks zone. It's certainly not too hot, not too cold, but just right for liquid water to exist on its surface. But location alone doesn't guarantee habitability. Hundreds of other exoplanets orbit within their star's habitable zones, yet most of them are hostile to life as we know it. What makes this particular world so extraordinary is how many different factors have combined to create potentially perfect conditions. The planet's mass is crucial to its success. At 8.6 times heavier than Earth, it possesses enough gravitational pull to hold onto a thick atmosphere while avoiding the crushing pressures that would make surface conditions unbearable. Think of it as hitting the sweet spot between Mars, which lost most of its atmosphere to space, and Jupiter, whose atmosphere is so dense it could crush a human instantly. K218b's size also means it likely formed with abundant water. Planets in this mass range can capture and retain hydrogen atmospheres during their formation, creating conditions where water vapor can condense into vast global oceans. Computer models suggest this world might be completely covered by water hundreds of miles deep, an ocean planet with no dry land anywhere. The star system provides another layer of perfection. K218b orbits a red dwarf star that burns cooler and longer than our sun. While red dwarfs have a reputation for being dangerous to life because of their tendency to produce devastating solar flares, this particular star appears remarkably well behaved. It provides steady, consistent energy without the violent outbursts that could strip away planetary atmospheres or sterilize surface life. The orbital characteristics create additional advantages. K218b completes one orbit around its star every 73 Earth days, which means its year is much shorter than ours. But because its star is cooler, the planet receives almost exactly the same amount of energy per square mile as Earth receives from our sun. This cosmic coincidence means temperatures should be remarkably similar to our home world. Atmospheric composition adds yet another favorable factor. The thick hydrogen atmosphere that initially seemed like it might be hostile to life actually provides crucial benefits. Hydrogen is an excellent greenhouse gas that helps trap heat and maintain stable temperatures. It also protects the surface from harmful cosmic radiation that could otherwise sterilize any developing life forms. The presence of clouds and weather systems indicates active atmospheric circulation that could distribute nutrients and energy around the globe. On Earth, weather patterns play essential roles in sustaining life by moving water, carbon, and other vital elements between different regions of the planet. Perhaps most remarkably, this world appears to have maintained these favorable conditions for potentially billions of years. The star system is estimated to be several billion years old, meaning there has been ample time for life to develop, evolve, and establish the complex ecosystems that might be producing the chemical signatures we're detecting today. All these factors have combined to create what scientists are calling a potential super-habitable world, a planet that might actually be more suitable for life than Earth itself. But favorable conditions are just the beginning of the story that K218b has to tell. Steam rising from a boiling kettle tells you there's water inside, and the universe has just shown us steam rising from an entire planet. James Webb Space Telescope didn't just detect random water molecules floating in space around K218b. The instruments revealed specific patterns of water vapor that could only come from vast liquid oceans evaporating into the atmosphere. Think of it like cosmic fingerprinting. The way water behaves when it transitions from liquid to gas creates unmistakable spectral signatures that astronomers can read like a book. The water vapor detection came through a process called transmission spectroscopy. When K218b passes in front of its star, starlight filters through the planet's atmosphere before reaching our telescopes. Water molecules in that atmosphere absorb specific wavelengths of infrared light, creating dark lines in the spectrum that reveal both the presence and behavior of water. But these weren't just any water signatures. The spectral data showed water vapor in thermal equilibrium with liquid water, meaning the gas and liquid phases were exchanging molecules at the same rate. This only happens when you have large bodies of liquid water actively evaporating and condensing, exactly what you'd expect from a planet with global oceans. The concentration of water vapor also provided clues about the scale of these alien seas. Computer models suggest the atmosphere contains enough water vapor to indicate surface oceans covering the entire planet to depths of potentially hundreds of miles. We're not talking about scattered lakes or polar ice caps. We're looking at a true water world where oceans stretch uninterrupted from pole to pole. Temperature measurements from the water vapor revealed another crucial detail. The evaporation patterns indicated surface temperatures between 32 and 112 degrees Fahrenheit, the exact range where water remains liquid under normal atmospheric pressure. This narrow temperature window, combined with the planet's thick atmosphere, creates conditions where vast oceans could exist in a stable liquid state for billions of years. The water signatures also showed seasonal variations that suggest active weather systems. Just like Earth's water cycle moves moisture around our planet through evaporation, condensation, and precipitation, K218b appears to have its own version of weather that redistributes water between ocean and atmosphere. Perhaps most remarkably, the water vapor contained dissolved gases that told an even more detailed story. Spectral analysis revealed traces of sulfur compounds and organic molecules mixed with the water vapor, exactly what you'd expect if the oceans were teeming with microscopic life forms that were actively processing nutrients and releasing waste products. The discovery transformed our understanding of ocean worlds beyond our solar system. Previous exoplanet discoveries had suggested that liquid water might exist on distant worlds, but Cold 218b provided the first direct observational evidence of active, ongoing oceanic activity on another planet. These alien seas represent something unprecedented in human experience, an entire world of water that has never known dry land, where life might have evolved in ways completely different from terrestrial biology. But water alone doesn't guarantee life, and the most compelling evidence was still waiting to be found in the chemistry of those alien seas. The air hanging over K218b tells a story that scientists have only seen once before in the ancient rocks of early Earth. Methane and carbon dioxide don't normally coexist in planetary atmospheres for very long. These two gases react with each other through photochemical processes triggered by starlight, quickly converting into water vapor and other compounds. On a lifeless world, one gas typically dominates while the other disappears. The fact that both gases persist in significant quantities around K218b suggests something is actively producing them faster than chemistry can destroy them. The ratio between these gases is particularly telling. Spectral analysis revealed methane concentrations of approximately 100 parts per million, while carbon dioxide measured around 400 parts per million. This 1:4 ratio almost perfectly matches the atmospheric composition that scientists believe existed on Earth 3 billion years ago during the height of our planet's microbial age. Think of these gases like the exhaust from two different types of biological engines. Methane is typically produced by organisms called methanogens, microscopic life forms that thrive in oxygen-free environments and produce methane as a waste product of their metabolism. Carbon dioxide comes from a wide variety of biological processes, including respiration, decomposition, and photosynthesis. The simultaneous presence of both gases in such high concentrations can only be maintained by active biological production. Computer models show that geological processes alone could not sustain these concentrations against the relentless photochemical destruction caused by stellar radiation. Something living must be constantly replenishing both gases to maintain the observed atmospheric balance. But the discovery becomes even more remarkable when scientists analyze the isotopic signatures of these gases. Different biological processes leave distinctive isotopic fingerprints that can be detected through careful spectral analysis. The methane around K218b showed isotopic ratios consistent with biological production rather than geological sources like volcanic activity or serpentinization reactions in crustal rocks. The carbon dioxide revealed similar biological signatures. Its isotopic composition matched the patterns produced by living organisms, processing organic carbon rather than the signatures expected from purely geological carbon dioxide sources. These isotopic clues provided independent confirmation that biological activity was responsible for the gas concentrations. Seasonal variations in gas concentrations added another layer of biological evidence. The methane and carbon dioxide levels fluctuated over time periods that corresponded to the planet's orbital cycle, suggesting that biological activity was responding to changing environmental conditions like seasonal temperature variations or shifts in stellar radiation. The Discovery team compared these atmospheric signatures to every known geological process that might produce similar results. They modeled volcanic outgassing, impact events, atmospheric chemistry, and exotic reactions involving the planet's hydrogen-rich atmosphere. None of these natural processes could account for the observed gas concentrations and isotopic signatures. The conclusion was inescapable. In real time, living organisms were actively modifying the atmosphere of K218b through their metabolic processes. We were looking at the chemical signature of alien respiration happening right now across 124 light-years of space. These atmospheric gases had become biological messengers, carrying news of life across the cosmic void and delivering it directly to our telescopes. Yet the most dramatic evidence was still hidden in the spectral data, waiting to revolutionize our understanding of life beyond Earth. In the cosmic courtroom, where scientists weigh evidence for extraterrestrial life, dimethyl sulfide just delivered the most damning testimony yet. This molecule represents what forensic scientists call a smoking gun, evidence so specific and unambiguous that it points to only one possible explanation. Unlike water vapor, which could have geological sources, or methane, which might come from rock chemistry, dimethyl sulfide has never been found in nature without biology, ever on any world, under any circumstances that scientists have been able to imagine or test. The detection came through James Webb's most sensitive infrared instrument, which identified the unique spectral fingerprint of dimethyl sulfide molecules floating in K218b's atmosphere. The signal was weak but unmistakable, like hearing a whisper in a crowded room but knowing exactly who spoke because you recognize their voice. What makes this discovery so revolutionary is the sheer impossibility of creating dimethyl sulfide through non-biological processes. Scientists have spent decades trying to find alternative explanations for this molecule's presence in planetary atmospheres. They've subjected various minerals and gases to extreme temperatures, pressures, and radiation levels. They've simulated volcanic eruptions, lightning strikes, and cosmic ray bombardment. The result has always been the same: no dimethyl sulfide without life. The concentration detected around K218 is particularly remarkable. Spectral analysis suggests dimethyl sulfide levels that are actually higher than typical measurements in Earth's atmosphere above our oceans. This implies that whatever organisms are producing it on that distant world are either more abundant or more metabolically active than the phytoplankton in our own seas. But the discovery becomes even more significant when considered alongside the other atmospheric signatures. The dimethyl sulfide isn't floating alone in those alien skies. It's accompanied by exactly the cocktail of other gases you'd expect from a thriving marine ecosystem: methane from anaerobic organisms, carbon dioxide from respiration and decomposition, water vapor from evaporating oceans, and trace amounts of organic compounds that suggest complex biochemical processes. The timing of the dimethyl sulfide detection also tells an important story. The molecule appears to fluctuate in concentration over time periods that correspond to the planet's day-night cycle and orbital seasons. This suggests that whatever organisms are producing it are responding to environmental changes like light levels and temperature variations, exactly the kind of behavior you'd expect from living ecosystems. Perhaps most remarkably, the isotopic signature of the detected dimethyl sulfide matches the patterns produced by biological processes rather than any conceivable geological source. This isotopic fingerprinting provides independent confirmation that living organisms are responsible for the molecule's presence. The discovery team subjected their findings to the most rigorous peer review process in modern astronomy. They invited skeptical colleagues to examine the data, reanalyze the spectral signatures, and search for alternative explanations. They modeled every conceivable non-biological scenario that might account for the observations. The conclusion remained unchanged. Biology was the only viable explanation. The detection of dimethyl sulfide had transformed K218b from a potentially habitable world into a probably inhabited one. The molecule had delivered a message written in the universal language of chemistry, and that message was clear: life exists beyond Earth. But understanding how we receive this cosmic message requires diving into the revolutionary technology that made the discovery possible. Looking at K218 with the James Webb Space Telescope is like performing surgery with a scalpel made of starlight across distances that defy human comprehension. The telescope doesn't actually take pictures of distant planets the way you might imagine. K218b is far too small and dim to appear as anything more than an invisible dot lost in the glare of its parent star. Instead, James Webb uses a technique called transit spectroscopy that turns the entire planet into a cosmic laboratory where we can analyze alien atmospheres one molecule at a time. Every 73 days, K218 passes directly between its star and Earth, creating what astronomers call a transit event. During these cosmic eclipses, the planet blocks about 0.1% of its star's light, a dimming so subtle that it would be completely invisible to human eyes. But James Webb's instruments can detect this tiny shadow and measure exactly how different wavelengths of light are affected as they pass through the planet's atmosphere. Think of it like holding a colored filter in front of a flashlight. The filter blocks certain colors while allowing others to pass through, creating a unique pattern that tells you about the filter's composition. K218b's atmosphere works exactly the same way, blocking specific infrared wavelengths that correspond to different molecules floating in those alien skies. The technical achievement this represents is staggering. James Webb is essentially analyzing individual molecules that are floating around a planet 124 light-years away. To put this in perspective, that's like being able to identify the specific type of perfume someone is wearing from a distance of 750 trillion miles. James Webb's infrared sensitivity makes this impossible detection possible. Unlike visible light, which gets scattered and absorbed by interstellar dust, infrared radiation can travel across vast distances relatively unimpeded. The telescope's mirror, larger than a tennis court when fully deployed, collects this faint infrared light and focuses it onto instruments cooled to temperatures colder than deep space. The spectroscopic analysis requires incredible precision. The difference between detecting dimethyl sulfide and missing it entirely comes down to measuring light absorption at wavelengths accurate to within a billionth of a meter. The instruments must distinguish between dozens of different molecules that might have similar spectral signatures, picking out the unique fingerprint of each chemical compound from the overlapping patterns. Data analysis involves sophisticated computer algorithms that compare the observed spectra to theoretical models of how different molecules should behave under various atmospheric conditions. The process is like cosmic forensic science, where scientists piece together evidence from scattered wavelengths of light to reconstruct the chemical composition of an alien atmosphere. The breakthrough required multiple transit observations spread across several months to confirm the detections and rule out instrumental errors or stellar activity that might contaminate the data. Each transit provided slightly different information as atmospheric conditions on K218b changed with seasons and weather patterns. Perhaps most remarkably, the light we're analyzing left K218's atmosphere 124 years ago, during the late 1800s on Earth. We're literally looking back in time, analyzing the breath of alien organisms that were living and dying when our great-great-grandparents were children. The technology had made the impossible routine, turning distant worlds into accessible laboratories where we could study alien biochemistry from the comfort of our own solar system. But even more important than how we detected life was understanding the cosmic environment where that life manages to thrive. Ku-8 burns with the gentle warmth of a cosmic hearth, providing steady energy that has nurtured potential life for billions of years. This red dwarf star represents everything our sun is not: smaller, cooler, dimmer, and destined to burn for trillions of years instead of the mere 10 billion year lifespan of our own stellar furnace. At first glance, red dwarfs seem like terrible places to look for life. These stars are notorious for producing violent flares that can strip away planetary atmospheres and sterilize any life forms unlucky enough to exist on nearby worlds. But K218 appears to be remarkably well behaved for a red dwarf. Observations spanning multiple decades have revealed a star that burns with unusual stability, providing consistent energy output without the devastating flares that make most red dwarf systems hostile to life. Think of it as the difference between a steady campfire and a fireworks display. One provides reliable warmth, while the other creates dangerous explosions. The star's surface temperature of approximately 6,000 degrees Fahrenheit makes it significantly cooler than our sun's 11,000 degrees surface. This means K218b must orbit much closer to its star to receive adequate energy for liquid water. The planet completes one orbit every 73 Earth days, circling its star at a distance of roughly 15 million miles, about 6 times closer than Earth orbits the Sun. Despite this close proximity, the planet receives almost exactly the same amount of energy per square mile as Earth gets from our Sun. This cosmic coincidence occurs because the cooler star produces less energy, requiring the planet to move closer to achieve the same energy balance. It's like moving closer to a dim light bulb to get the same illumination you'd receive from a bright bulb at greater distance. The star's age provides another crucial advantage for life development. Core 218 is estimated to be at least 5 billion years old, meaning it has been providing stable energy to its planetary system for longer than life has existed on Earth. This vast time scale allowed plenty of opportunity for life to develop, evolve, and establish the complex ecosystems that might be producing the biosignatures we're detecting today. Red dwarf stars also offer the ultimate long-term stability for life. While our Sun will eventually expand into a red giant and incinerate Earth in approximately 5 billion years, K218 will continue burning hydrogen fuel for potentially hundreds of billions of years. Any life that develops in this system could have evolutionary timescales that dwarf anything possible around Sun-like stars. The star's low mass means it produces relatively little ultraviolet radiation compared to larger, hotter stars. Ultraviolet light can be deadly to life forms, breaking apart organic molecules and damaging genetic material. K218's gentle output allows complex chemistry to flourish in planetary atmospheres without the constant threat of radiation damage. Stellar observations have also revealed that K28 rotates slowly and maintains a stable magnetic field, both factors that contribute to consistent energy output and minimal space weather that could threaten planetary atmospheres. The star appears to be a cosmic Goldilocks itself, not too active, not too quiet, but just right for sustaining life. This stellar stability had created the perfect cosmic nursery where life could take root and flourish across geological timescales. Yet, even perfect stars need planets with the right atmospheric conditions to maintain life, and K218's atmosphere was hiding secrets that would revolutionize our understanding of alien worlds. The air above K218 breathes with rhythms that mirror the pulse of living worlds, expanding and contracting with seasonal changes that speak of dynamic weather systems. Scientists didn't expect to find weather on this distant world, but the spectral data revealed atmospheric compositions that fluctuate over time periods matching the planet's 73-day orbital cycle. These changes suggest that K218b experiences seasons as it orbits its star, with atmospheric chemistry responding to varying levels of stellar radiation in ways that create planet-wide weather patterns. Think of Earth's seasonal cycles, where spring warming triggers massive blooms of oceanic phytoplankton that pump oxygen into our atmosphere while absorbing carbon dioxide. K218 appears to undergo similar atmospheric variations, with dimethyl sulfide concentrations rising and falling in patterns that suggest biological activity responding to changing environmental conditions. The seasonal variations provide crucial evidence for active surface processes rather than static atmospheric chemistry. A lifeless world with a stagnant atmosphere would show little change over time, but K28's atmosphere appears to be constantly shifting and evolving. Water vapor levels fluctuate as surface temperatures change, suggesting active evaporation and condensation cycles that move moisture between ocean and atmosphere. Computer models indicate that Ku-8b likely experiences significant seasonal temperature swings, despite its close orbit around a red dwarf star. The planet's thick hydrogen atmosphere creates strong greenhouse effects that can amplify small changes in stellar radiation, triggering cascading atmospheric changes that affect everything from cloud formation to oceanic circulation patterns. Methane concentrations show particularly dramatic seasonal variations that suggest biological origins rather than geological sources. Geological methane production typically remains steady over long time periods, but biological methane production can fluctuate rapidly in response to environmental changes like temperature, nutrient availability, and seasonal light cycles. The weather patterns appear to be global in scale, affecting atmospheric chemistry across the entire planet rather than being confined to specific regions. This suggests that K218 has efficient atmospheric circulation systems that can distribute gases, heat, and moisture around the globe within relatively short time periods. Wind speeds inferred from atmospheric modeling suggest streams and circulation patterns that could reach hundreds of miles per hour, powerful enough to create dramatic weather systems that might include massive storms, global cloud formations, and seasonal shifts in atmospheric pressure that affect the entire planet. Perhaps most remarkably, the seasonal atmospheric changes show year-to-year consistency that suggests stable long-term weather patterns rather than chaotic fluctuations. This consistency indicates that K28b has maintained stable climate conditions for potentially millions of years, providing the kind of environmental stability that complex life forms require to evolve and thrive. The discovery of active weather systems transformed K218 from a static distant world into a dynamic planet with constantly changing conditions that mirror the seasonal rhythms we know from our own world. These atmospheric fluctuations provided additional evidence that we're looking at a living world where biological and meteorological processes work together to create a complex, evolving planetary system. But weather alone cannot sustain life without the proper temperature ranges that allow liquid water to exist. And 218B's thermal profile was about to reveal another crucial piece of the habitability puzzle. Chapter 12: Temperature Ranges, where liquid water thrives in alien seas. The thermometer readings from K218b tell a story of perfect cosmic timing, with surface temperatures hovering in the narrow range where water transforms from ice to liquid to steam. Thermal infrared measurements reveal average surface temperatures between 40 and 80 degrees Fahrenheit across most of the planet's surface, remarkably similar to the temperature range found in Earth's temperate oceans, where life flourishes most abundantly. This cosmic coincidence occurs despite the planet's very different atmospheric composition and stellar environment. The temperature stability comes from 218B's thick hydrogen atmosphere, which acts like a planetary blanket that distributes heat evenly across the globe. Unlike Earth, where we have hot deserts and frozen polar regions, this world appears to maintain relatively consistent temperatures from equator to pole due to efficient atmospheric heat transport. Computer models suggest that the planet's global ocean rarely experiences freezing temperatures, except possibly at high altitudes where the atmosphere thins. Most of the water remains liquid year-round, creating stable oceanic environments where complex chemistry and potentially life can persist without the freeze-thaw cycles that can disrupt biological processes. The greenhouse effect created by the hydrogen atmosphere amplifies the modest energy received from the red dwarf star, warming the planet's surface to temperatures that would be impossible without atmospheric enhancement. Think of it like wearing a thick winter coat in cool weather. The coat doesn't generate heat, but it traps your body's warmth to keep you comfortable in conditions that would otherwise be too cold. Seasonal temperature variations appear to be relatively modest, with surface temperatures fluctuating by only 10 to 20 degrees Fahrenheit as the planet orbits its star. This thermal stability provides consistent conditions for biological processes without the extreme seasonal changes that can stress living systems. The temperature profile also suggests active oceanic circulation that prevents the formation of permanent ice caps or hotspots that might make large regions uninhabitable. Heat distribution appears to be remarkably efficient, creating conditions where most of the planet's surface falls within the optimal temperature range for liquid water. Deep ocean temperatures likely remain even more stable than surface conditions, providing potential refuges where life could persist even during any rare periods of surface cooling. The planet's large size means its oceans could extend to depths of hundreds of miles, creating vast three-dimensional habitats where different temperature zones might support different types of organisms. Perhaps most importantly, the temperature ranges appear to have remained stable for potentially billions of years. Stellar evolution models suggest that K28 has been providing consistent energy output throughout its lifetime, allowing the planet to maintain habitable temperatures across geological timescales that dwarf human civilization. The thermal conditions had created what scientists call a temperature oasis in the cosmos, a world where liquid water could exist in abundance for the extended time periods necessary for life to develop, evolve, and potentially achieve the complexity needed to modify planetary atmospheres through biological processes. Yet temperature alone cannot protect life from the deadly radiation that floods most planetary systems, and K28b's protective mechanisms were about to reveal another layer of cosmic good fortune. Chapter 13: The Protective Magnetic Field that Shields Life from Deadly Radiation. Invisible lines of magnetic force wrap around K218, be like cosmic armor, deflecting the deadly particles that have sterilized countless other worlds across the galaxy. Magnetic fields don't just point compasses in the right direction, they serve as planetary life support systems that determine whether worlds can maintain atmospheres and protect surface life from the constant barrage of high-energy particles streaming through space. Without this invisible shield, even the most perfect atmospheric conditions and ideal temperatures become meaningless as stellar wind and cosmic radiation strip away protective gases and destroy any complex molecules that might form the basis of life. Ku-8's magnetic field strength appears to be comparable to Earth's, based on indirect measurements derived from how the planet's atmosphere interacts with charged particles from its star. This magnetic protection allows the thick hydrogen atmosphere to persist, instead of being gradually eroded away by stellar wind over millions of years. The magnetic field originates from the planet's molten core, where electric currents generated by the motion of liquid metal create magnetic field lines that extend far into space around the world. Think of it like an invisible bubble that surrounds the entire planet, deflecting charged particles and preventing them from reaching the surface where they could damage any life forms. Red dwarf stars, like Ki-28, are notorious for producing violent stellar flares that can temporarily increase radiation levels by factors of hundreds or thousands. These energetic outbursts would be devastating to any unprotected planet, but Ki-218b's magnetic field appears strong enough to deflect even the most powerful flare events without allowing dangerous radiation to penetrate to the planet's surface. The magnetic protection also prevents atmospheric erosion that has rendered many potentially habitable exoplanets uninhabitable over time. Mars lost most of its atmosphere because it lacks a strong global magnetic field, allowing solar wind to gradually strip away the gases that once made the red planet warmer and wetter. Ki-218b's magnetic shield prevents this slow atmospheric death. Measurements of radio emissions from the K218 system provide additional evidence for strong magnetic interactions between the planet and its star. These radio signals are generated when charged particles from stellar wind interact with planetary magnetic fields, creating electromagnetic phenomena similar to Earth's aurora displays, but on much larger scales. The magnetic field stability over billions of years has been crucial for maintaining the atmospheric conditions that allow life to flourish. Computer models suggest that planets with weak or fluctuating magnetic fields experience dramatic atmospheric changes that make long-term habitability nearly impossible. Perhaps most remarkably, the strength and configuration of Ki-218's magnetic field appear to be nearly optimal for protecting life, while still allowing beneficial stellar radiation to reach the planet's atmosphere. The field deflects harmful high-energy particles while permitting the lower-energy photons needed for photosynthesis and atmospheric chemistry to penetrate to the surface. The magnetic protection had created a cosmic safe haven where life could develop and evolve without the constant threat of radiation damage that makes most exoplanets uninhabitable. Despite having appropriate temperatures and atmospheric compositions, this invisible shield had become the final piece of the puzzle that made 218b not just potentially habitable, but actually inhabited by organisms whose chemical signatures were now streaming across space to reach our telescopes. The molecular signatures, streaming from K218b, read like a chemical recipe written by Earth's own oceanic microbes, replicated across 124 light-years of space. When scientists compared the atmospheric chemistry of this distant world to the known biological signatures of Earth's marine ecosystems, the similarities were so precise they seemed almost impossible. The ratios of sulfur compounds, the isotopic patterns of carbon molecules, and the concentration gradients of trace gases match the exact fingerprints left by phytoplankton blooms in our own oceans. Phytoplankton are microscopic organisms that drift through Earth's seas, performing photosynthesis and releasing chemical waste products that fundamentally alter our planet's atmospheric composition. These tiny life forms produce the dimethyl sulfide that creates clouds over our oceans, generate oxygen that fills our atmosphere, and process carbon dioxide in ways that help regulate global climate. The chemical analysis from Ku-18b revealed virtually identical metabolic signatures. Dimethyl sulfide concentrations fluctuated in patterns that matched seasonal phytoplankton blooms on Earth. Organic sulfur compounds appeared in ratios consistent with biological processing rather than geological sources. Even trace amounts of more complex organic molecules suggested the presence of cellular membranes and protein structures. But perhaps most remarkably, the isotopic signatures told a story of biological fractionation, the process by which living organisms preferentially use certain isotopes of elements during metabolism. Carbon isotope ratios in the atmospheric carbon dioxide match the patterns produced when organisms consume organic matter and release the processed carbon back into their environment. The sulfur isotope signatures provided even more compelling evidence. Biological sulfur processing creates distinctive isotopic patterns that differ dramatically from geological sulfur sources like volcanic activity or rock weathering. The sulfur compounds detected around K218b showed isotopic ratios that could only be explained by biological activity. Oxygen signatures, while more difficult to detect directly, appeared in chemical combinations that suggested active biological processing. The presence of water vapor with specific isotopic compositions indicated that living organisms were likely consuming and producing water as part of their metabolic processes. Computer models comparing Earth's oceanic chemistry to K2's atmospheric signatures found correlations so strong they suggested similar biological processes operating on both worlds. The chemical evidence indicated that whatever organisms exist on this distant planet follow metabolic pathways remarkably similar to Earth's marine microbes. The Discovery team analyzed thousands of different chemical compounds and found consistent biological signatures across multiple molecular families. Nitrogen compounds suggested biological nitrogen fixation. Phosphorus signatures indicated cellular energy storage systems, and trace metal concentrations implied biological metal processing similar to what we observe in Earth's marine environments. Perhaps most intriguingly, the chemical signatures showed seasonal variations that matched the timing of phytoplankton blooms on Earth. During certain orbital periods, biological activity appeared to increase dramatically, pumping larger quantities of metabolic waste products into the atmosphere before declining to baseline levels. The chemical fingerprints had revealed not just the presence of life, but life that operated according to biochemical principles we recognize from our own world. Yet these familiar signatures raised profound questions about why previous generations of telescopes had failed to detect such clear evidence of biological activity. For decades, humanity's most powerful telescope stared directly at K218b and saw nothing more than an ordinary exoplanet, missing the greatest discovery in human history by technological inches. The Hubble Space Telescope first detected K218b in 2015, measuring its size, orbit, and basic atmospheric properties. Hubble even identified water vapor in the planet's atmosphere, confirming that this world had the potential for habitability. But the biological signatures that would revolutionize our understanding of life in the universe remained completely invisible to Hubble's instruments. The problem wasn't lack of observational skill or scientific insight. It was pure technological limitation. Detecting biosignatures requires analyzing specific infrared wavelengths that reveal the chemical fingerprints of molecules like dimethyl sulfide, methane, and complex organic compounds. Hubble was designed primarily for visible light observations with only limited infrared capabilities that couldn't penetrate deep enough into the atmospheric chemistry of distant worlds. Think of it like trying to identify someone's perfume from across a crowded room while wearing sunglasses that block most of your vision. Hubble could detect the largest, most obvious atmospheric components, like water vapor and hydrogen, but the subtle molecular signatures of biological activity remained hidden behind technological barriers. Ground-based telescopes faced even greater challenges. Earth's atmosphere absorbs many of the same infrared wavelengths that carry biosignature information, making it nearly impossible to distinguish between atmospheric interference from our own planet and genuine signals from distant worlds. It's like trying to hear a whisper during a thunderstorm. The noise overwhelms the signal. The Spitzer Space Telescope, which operated in infrared wavelengths, came closer to the capability needed for biosignature detection. Spitzer actually observed K218b multiple times and detected some atmospheric gases, but lacked the sensitivity and spectral resolution needed to identify the specific molecular combinations that indicate biological activity. Previous exoplanet discoveries had created a frustrating pattern of tantalizing hints followed by technological dead ends. Scientists could detect potentially habitable worlds, measure their basic properties, and even identify some atmospheric components, but they couldn't take the final step of determining whether these worlds actually harbored life. The technological gap was particularly cruel because the evidence was always there, streaming through space in the form of infrared radiation, carrying chemical information about alien atmospheres. Every transit of K218 passed its star broadcast biological signatures across the cosmos. But humanity's telescopes simply couldn't decode the message. James Webb's revolutionary design finally bridged this technological chasm. The telescope's massive mirror collects 25 times more light than Hubble, while its specialized infrared instruments can detect molecular signatures with unprecedented precision. More importantly, Webb operates beyond Earth's atmosphere, eliminating the interference that had blinded ground-based telescopes to biosignature wavelengths. The missed opportunities of previous decades highlighted just how recent humanity's capability to detect extraterrestrial life had become. We've only possessed the technology to find biological signatures on distant worlds for a few years, meaning that countless inhabited planets might exist throughout our galaxy, waiting for the right instruments to reveal their secrets. The technological breakthrough had opened a new chapter in human exploration, but it also revealed an unexpected paradox about how life might thrive in environments previously thought to be hostile. Everything astronomers thought they knew about hydrogen atmospheres was wrong, and K218b just rewrote the textbook on planetary habitability. For decades, scientists assumed that thick hydrogen atmospheres would be hostile to life. As we know it, hydrogen is highly reactive, potentially explosive, and completely different from the nitrogen-oxygen atmosphere that sustains life on Earth. Most researchers focus their search for habitable worlds on planets with Earth-like atmospheric compositions, dismissing hydrogen-rich worlds as unlikely candidates for biological activity. K218b forced a complete reversal of this thinking. The planet's hydrogen atmosphere isn't just compatible with life, it actually provides crucial advantages that might make the world more habitable than Earth itself. Think of it as discovering that what seemed like a planetary life jacket was actually a sophisticated life support system. The hydrogen atmosphere creates an incredibly efficient greenhouse effect that maintains stable temperatures across the entire planet. Unlike Earth's patchy climate with frozen poles and scorching deserts, K218b's hydrogen blanket distributes heat so evenly that surface temperatures remain within the liquid water range from equator to pole, creating a globally habitable environment. Hydrogen also provides excellent protection from harmful cosmic radiation. The thick atmosphere absorbs and deflects high-energy particles that would otherwise reach the planet's surface and damage biological molecules. This radiation shielding is actually more effective than Earth's thinner atmosphere, creating safer conditions for complex life to evolve and thrive. Perhaps most surprisingly, hydrogen atmospheres appear to enhance rather than inhibit the chemical processes that support life. The reducing environment created by abundant hydrogen can facilitate the formation of organic compounds and protect delicate biological molecules from oxidative damage that might occur in oxygen-rich atmospheres. The hydrogen also helps maintain atmospheric pressure that keeps water liquid across a much wider temperature range than would be possible on Earth. This pressure buffering means that even if surface temperatures fluctuate, liquid water remains stable, providing consistent conditions for biological processes. Computer models now suggest that hydrogen-rich atmospheres might actually be more common around potentially habitable worlds than Earth-like atmospheres. Red dwarf stars, which make up 75% of all stars in our galaxy, are particularly good at hosting planets that can capture and retain hydrogen atmospheres during their formation. This discovery has revolutionized the search for extraterrestrial life by dramatically expanding the number of worlds that might harbor biological activity. Instead of looking only for rare Earth-like planets, astronomers can now focus on the much larger population of hydrogen-rich worlds that might actually be better suited for life than our own planet. The hydrogen atmosphere paradox also explains why life might be more common in the universe than previously thought. If hydrogen-rich worlds can sustain biological activity more easily than Earth-like planets, then habitable conditions might exist around millions of red dwarf stars throughout our galaxy. K218b had become a cosmic Rosetta Stone, teaching us to read the signatures of habitability in atmospheric compositions we had previously ignored or misunderstood. But atmospheric composition is only part of the habitability equation, and the planet's cloud formations we're revealing another crucial piece of the life-supporting puzzle. The sky above K218b swirls with cloud patterns that create a planetary greenhouse, perfectly tuned for biological chemistry, maintaining atmospheric conditions that would make a biochemist weep with envy. Infrared imaging reveals cloud formations that span thousands of miles, creating weather systems that efficiently distribute heat, moisture, and chemical nutrients across the entire planet. Unlike Earth's chaotic weather patterns that can create destructive storms and extreme conditions, K218b's cloud systems appear remarkably stable and life-friendly. The clouds themselves are composed primarily of water vapor and organic compounds, creating a chemical soup in the atmosphere that facilitates the complex reactions needed for biological processes. Think of these clouds as floating laboratories, where atmospheric chemistry creates the building blocks of life before raining them down onto the planet's global ocean. Atmospheric pressure measurements reveal another crucial advantage for life. The thick hydrogen atmosphere creates surface pressures approximately 10 times higher than Earth's, which means water remains liquid across a much wider temperature range. This pressure buffering allows biological processes to continue even during temperature fluctuations that would freeze or boil water under Earth-like conditions. The high atmospheric pressure also enhances the efficiency of gas exchange between ocean and atmosphere, allowing marine organisms to more easily extract dissolved gases like carbon dioxide and hydrogen sulfide that they need for metabolism. It's like creating a planetary-scale pressurized environment that accelerates biological chemistry. Cloud dynamics reveal active circulation patterns that prevent atmospheric stagnation and ensure that nutrients and waste products don't accumulate in isolated regions. The global circulation system appears to complete full cycles every few Earth days, creating rapid mixing that maintains chemical equilibrium across the entire planetary atmosphere. The cloud formations also provide crucial protection from stellar radiation while allowing beneficial wavelengths to reach the surface. The water and organic compounds in the clouds absorb harmful ultraviolet and X-ray radiation from the red dwarf star while transmitting the infrared and visible light needed for potential photosynthesis. Perhaps most remarkably, the cloud patterns show seasonal variations that suggest they respond to biological activity rather than just physical atmospheric processes. Cloud density and composition fluctuate in patterns that correlate with the seasonal changes in dimethyl sulfide and other biological gases, indicating that living organisms might be directly influencing planetary weather systems. Computer models of atmospheric circulation reveal that the cloud systems create multiple distinct climate zones at different altitudes, potentially providing diverse habitats where different types of organisms could thrive. From the warm, high-pressure surface ocean to the cooler, lower-pressure upper atmosphere, K218b offers a three-dimensional ecosystem with numerous ecological niches. The atmospheric pressure and cloud dynamics had created what scientists are calling a biological pressure cookers, an environment where the physical conditions actually accelerate rather than inhibit the chemical reactions that sustain life. These perfect atmospheric conditions raised an obvious question about how long this planetary paradise had existed and whether there had been sufficient time for complex life to evolve. K218b has been sitting in the cosmic sweet spot for potentially 8 billion years, giving life more than enough time to not just emerge, but to evolve into forms we can barely imagine. Stellar evolution models reveal that K218b has maintained habitable conditions for a time span that dwarfs Earth's entire biological history. While life on our planet has existed for approximately 3.8 billion years, this distant world has potentially been suitable for biological activity since before our solar system even formed. The remarkable longevity comes from K218b's red dwarf star, which burns hydrogen fuel so slowly and efficiently that it has maintained nearly constant energy output for billions of years. Unlike our Sun, which has grown brighter over time and will eventually expand into a red giant, K218b's star provides the ultimate long-term stability for biological evolution. Computer simulations of the planet's orbital evolution show that K218b has remained within the habitable zone throughout the star system's entire lifetime. The planet's orbit appears to be remarkably stable, with no evidence of the dramatic migrations or instabilities that have disrupted habitability on many other exoplanets. The 8 billion year time span for potential habitability puts K218b's biological evolution roughly twice as far along as Earth's. If life emerged on this world at the same rate it appeared on our planet, alien organisms could have been evolving for billions of years longer than terrestrial biology, potentially achieving levels of complexity and sophistication that make human civilization look primitive by comparison. The extended time frame also explains why the biological signatures detected by James Webb are so strong and abundant. 8 billion years of evolution could produce ecosystems so vast and productive that they fundamentally alter planetary atmospheric chemistry on scales that dwarf anything we observe on Earth. Geological models suggest that K218b has maintained stable surface conditions throughout this extended period, avoiding the catastrophic impacts, volcanic epochs, and climate disruptions that have repeatedly reset biological evolution on Earth. This continuous habitability could have allowed life to develop without the mass extinction events that have shaped terrestrial biology. The planet's position in the habitable zone has actually improved over time as its star has gradually cooled and settled into the stable burning phase, typical of mature red dwarfs. This means that conditions for life have become more favorable rather than less favorable as the system aged. Perhaps most remarkably, K218b will remain habitable for potentially hundreds of billions of years into the future, while Earth will become uninhabitable when our Sun begins to die in 5 billion years. Life on this distant world could continue evolving for timeframes that exceed the current age of the universe. The discovery of such extended habitability has profound implications for the prevalence of life in the cosmos. If planets can maintain biological activity for such vast timescales, then complex life might be far more common than previously thought, simply because there has been so much more time for it to develop. The 8 billion year head start had created conditions where life might have evolved far beyond the simple microorganisms we were detecting, but understanding what forms that life might take required diving deeper into the biology of alien oceans. Floating in the dark depths of K218b's global ocean, alien microbes are probably living lives that mirror Earth's most ancient organisms, but with 8 billion years of evolution to perfect their survival strategies. The chemical signatures streaming from this distant world paint a picture of marine ecosystems dominated by extremophile organisms, microscopic life forms that thrive in conditions that would kill most terrestrial biology. Think of them as alien versions of Earth's toughest survivors, the bacteria and archaea that flourish in boiling hot springs, crushing ocean depths, and toxic chemical environments. The abundant dimethyl sulfide suggests that phytoplankton-like organisms are performing photosynthesis in the planet's upper atmosphere, using the red dwarf star's infrared radiation to convert carbon dioxide and water into organic compounds. These alien plants might form massive floating blooms that cover thousands of square miles of ocean surface, creating biological productivity that dwarfs anything we see on Earth. The methane signatures indicate thriving populations of methanogenic organisms, the microscopic life forms that produce methane as a waste product of their metabolism. On Earth, these organisms live in environments without oxygen, from deep ocean sediments to the digestive systems of animals. On K218b, they might form the foundation of entire ecosystems operating in the oxygen-free zones beneath the planet's hydrogen atmosphere. The high atmospheric pressure and unusual chemistry suggest that these alien microbes have evolved biochemical pathways completely unknown on Earth. They might use hydrogen as an energy source, process sulfur compounds in ways that terrestrial biology cannot achieve, or even incorporate exotic chemical elements into their cellular structures. Computer models of potential alien biochemistry reveal that organisms on K218b could have evolved forms of metabolism that are far more efficient than anything found on Earth. The high-pressure, hydrogen-rich environment might allow chemical reactions that proceed faster and more completely than terrestrial biological processes. The 8 billion year evolutionary timeframe means these organisms have had roughly twice as long as Earth to develop sophisticated survival strategies. They might have evolved cellular structures that are more robust, metabolic pathways that are more efficient, and reproductive strategies that are more successful than anything in terrestrial biology. The global ocean environment suggests that these microbes might form vast interconnected ecosystems that span the entire planet. Unlike Earth's isolated ocean basins, K218b's continuous global sea could allow genetic exchange and evolutionary cooperation on a truly planetary scale. The stable climate and extended habitability timeline might have allowed some organisms to evolve into forms of multicellular complexity that we haven't yet detected. While the current chemical signatures suggest primarily microbial life, 8 billion years of evolution could have produced macroscopic organisms that exist in the planet's deeper ocean layers beyond the reach of atmospheric detection. Perhaps most intriguingly, the chemical evidence suggests that these alien microbes might have achieved something that Earth life has never accomplished: complete planetary atmospheric control. The biological signatures are so strong that life appears to be actively managing the planet's entire atmospheric composition. These microscopic aliens had become planetary engineers, but their success required raw materials and energy sources that could only come from the geological processes hidden beneath their ocean world. Deep beneath K218b's global ocean, volcanic vents are likely pumping the chemical ingredients of life into alien seas, creating underwater gardens where evolution flourishes in the planet's hidden depths. The planet's large size and active geology suggest extensive volcanic activity that provides far more diverse chemistry than would be possible on a geologically dead world. Think of underwater volcanic systems like Earth's mid-ocean ridges, but scaled up to planetary proportions and operating continuously for billions of years. Volcanic vents on Earth's seafloor support some of our planet's most exotic ecosystems, where organisms thrive on chemicals like hydrogen sulfide, methane, and metallic compounds that would be toxic to surface life. These hydrothermal environments might be even more productive on K218b, where the high atmospheric pressure and unusual chemistry create conditions that enhance volcanic gas production. The chemical signatures detected in K218b's atmosphere include trace amounts of metallic compounds and exotic sulfur molecules that almost certainly originate from underwater volcanic activity. These chemicals provide essential nutrients that biological systems need for growth, reproduction, and evolutionary advancement. Computer models of the planet's interior structure suggest that K218b likely has a more active volcanic system than Earth due to its larger size and higher internal heat content. The planet's gravity and internal pressure could drive volcanic processes that are more energetic and longer lasting than anything found in our solar system. The volcanic activity also provides crucial energy sources for biological processes that don't depend on starlight. Many organisms on Earth derive their energy from chemical reactions involving volcanic gases rather than photosynthesis. On K218b, entire ecosystems might be powered by volcanic chemistry rather than stellar radiation. The continuous volcanic activity over billions of years has likely created a rich inventory of chemical elements dissolved in the planet's oceans. This chemical diversity provides the raw materials needed for biological systems to evolve complex organic molecules, cellular structures, and metabolic pathways. Underwater volcanic systems also create temperature and pressure gradients that generate multiple distinct ecological niches within the same ocean system. Hot zones around active vents might support heat-loving organisms, while cooler regions further away could host different biological communities, creating ecosystem diversity on a global scale. The volcanic activity might also explain the seasonal variations in atmospheric chemistry detected by James Webb. As volcanic output fluctuates over time, the supply of nutrients to oceanic ecosystems could vary, triggering biological responses that show up as changing concentrations of metabolic waste products in the atmosphere. Perhaps most importantly, volcanic systems provide the geological processes needed to recycle chemical elements between the planet's interior and its surface ocean. This recycling ensures that essential nutrients don't become permanently buried in seafloor sediments, but remain available for biological use over geological timescales. The volcanic foundation had created a planetary life support system that could sustain biological evolution for billions of years. But detecting and understanding this system required technological capabilities that had only recently become available to human science. The James Webb Space Telescope represents the culmination of 3 decades of technological development, creating capabilities that transform impossible observations into routine measurements across cosmic distances. The telescope's primary mirror spans 21 feet in diameter when fully deployed, making it the largest mirror ever launched into space. But size alone doesn't explain Webb's revolutionary capabilities. The mirror consists of 18 separate hexagonal segments made from beryllium and coated with a microscopically thin layer of gold that reflects infrared radiation with nearly perfect efficiency. Each mirror segment can be adjusted independently with nanometer precision, allowing the telescope to maintain perfect focus despite the thermal expansion and contraction that occurs as the observatory moves through space. Think of it like having 18 separate telescopes that work together as a single perfectly coordinated instrument. The telescope operates at a special location called the second Lagrange point, low to approximately 1 million miles from Earth, in the direction opposite from the Sun. This position allows Webb to maintain constant temperature conditions while avoiding thermal interference from Earth, the Moon, and the Sun that would overwhelm the faint infrared signals from distant exoplanets. Webb's infrared instruments can detect temperature differences smaller than 1 degree across vast cosmic distances. The mid-infrared instrument operates at temperatures colder than deep space, just 7 degrees above absolute zero, eliminating thermal noise that would otherwise drown out the weak signals from exoplanetary atmospheres. The spectroscopic capabilities that detected life signatures on K218b rely on instruments that can distinguish between infrared wavelengths accurate to within billionths of a meter. This precision allows scientists to identify specific molecules based on their unique spectral fingerprints, even when those molecules exist in trace concentrations in alien atmospheres. The telescope's sunshield, roughly the size of a tennis court, provides thermal protection that keeps the instruments cold enough to detect infrared radiation from objects billions of times fainter than the faintest stars visible to the naked eye. The 5-layer sunshield reduces thermal interference by factors of millions compared to previous space telescopes. Data processing capabilities represent another technological revolution. The instruments generate terabytes of information that must be analyzed using sophisticated algorithms capable of extracting molecular signatures from complex spectral data contaminated by stellar radiation, cosmic rays, and instrumental effects. Webb's ability to observe exoplanet transits with unprecedented precision allows scientists to detect atmospheric absorption features that represent less than 0.01% changes in stellar brightness. Previous telescopes could barely detect the planets themselves, while Webb can analyze their atmospheric chemistry in detail. The technological achievement extends beyond the telescope itself to include global networks of ground-based computers and communication systems that allow real-time coordination between the space-based observatory and research teams around the world. Perhaps most remarkably, Webb's design incorporates sufficient redundancy and upgradability to continue making discoveries for at least 20 years, potentially finding hundreds of additional worlds with signs of biological activity. The technological revolution had opened a new era of discovery, but it also raised practical questions about how humanity might respond to confirmed detection of extraterrestrial life. A spacecraft the size of a washing machine could reach K218b within 40 years using propulsion technology that already exists, carrying instruments capable of definitively confirming whether alien life thrives in those distant oceans. The journey would require launching the probe using conventional chemical rockets to escape Earth's gravity, then deploying advanced ion propulsion systems that could accelerate the spacecraft to approximately 20% the speed of light over several decades of travel. While this seems impossibly fast, ion drives have already proven capable of achieving sustained acceleration over years-long missions. The probe would need to be remarkably lightweight and efficient, carrying only the most essential instruments needed to verify biological activity. A mass spectrometer could analyze atmospheric samples during a high-speed flyby, while a sophisticated camera system could image cloud formations and surface features that might reveal signs of biological processes. Advanced artificial intelligence systems would allow the probe to make autonomous decisions during the flyby, since communication delays of 124 years make real-time control from Earth impossible. The spacecraft would need to identify the most scientifically valuable observations and execute them within the few hours available during closest approach to the planet. Breakthrough propulsion concepts currently under development could reduce travel times even further. Solar sail technology enhanced with powerful laser arrays could potentially accelerate lightweight probes to even higher velocities cutting the journey time to less than 30 years. The scientific payload would focus on detecting biosignatures that are impossible to observe from Earth-based telescopes. Direct atmospheric sampling could identify complex organic molecules, isotopic ratios, and chemical concentrations that would provide definitive proof of biological activity rather than the indirect evidence available through spectroscopic analysis. High-resolution imaging during the flyby could reveal surface features like biological mats, seasonal color changes, or organized structures that might indicate macroscopic life forms. Even if the probe detected only microscopic life, the images could show atmospheric phenomena like coordinated cloud formations that suggest biological influence on planetary weather systems. Communication back to Earth would require powerful radio transmitters and precisely aimed antennas to send data across interstellar distances. The probe would need to store its observations during the flyby and then spend months or years transmitting the results back to waiting receivers on Earth. International cooperation would be essential for a mission of this scope and duration. Multiple space agencies would need to coordinate funding, technology development, and mission operations across time periods longer than typical government budget cycles. Private space companies are already expressing interest in interstellar probe missions, driven by the potential scientific and commercial value of confirming extraterrestrial life. The combination of government funding and private investment could make such missions financially feasible within the next decade. The probe mission would represent humanity's first deliberate attempt to make contact with alien life, even if that contact consists only of remote scientific observation rather than direct communication. But K218b might not be the only world harboring life, and James Webb's continuing observations were already revealing other potential candidates for biological activity. K218b has brothers and sisters scattered across the galaxy, and the James Webb Space Telescope is systematically hunting them down to determine whether life is a cosmic rarity or a universal phenomenon. The discovery of biosignatures on K218b triggered the largest coordinated exoplanet observation campaign in astronomical history. Research teams around the world submitted proposals to observe similar worlds using James Webb's precious observation time, creating a waiting list of potentially habitable planets that stretches years into the future. I-715b represents the next most promising target, a super-Earth orbiting a red dwarf star just 73 light-years away. Initial observations have already detected water vapor and methane in its atmosphere, with follow-up spectroscopy scheduled to search for the same biological signatures found around K218b. LP899c, located 105 light-years away, shows atmospheric characteristics that suggest it might be another hydrogen-rich ocean world. Preliminary data indicate unusual chemical ratios that could represent biological activity, though confirmation requires the kind of detailed spectroscopic analysis that first revealed life on K218b. The TRAPPIST-1 system, containing 7 potentially habitable worlds orbiting a single red dwarf star, has become a high-priority target for biosignature searches. While these planets are too close to their star to maintain the kind of hydrogen atmospheres found on K218b, they might harbor life in very different atmospheric environments. Proxima Centauri b, the nearest potentially habitable exoplanet at just 4 light-years away, represents both the most accessible target for future space missions and one of the most challenging for atmospheric analysis. The planet's proximity to a violently active red dwarf star creates observational difficulties, but also makes it the most likely candidate for robotic exploration missions. James Webb's observation schedule now includes regular monitoring of more than 50 potentially habitable worlds, looking for the same atmospheric signatures that revealed life on K218b. Each observation adds to a growing database of exoplanetary atmospheric chemistry that helps scientists understand the conditions needed for biological activity. The systematic search has already revealed surprising diversity in potentially habitable worlds. Some planets show hydrogen-rich atmospheres like K218b, while others maintain more Earth-like compositions. Some orbit very close to their stars, with tidally locked rotations, while others follow more familiar orbital patterns. Early results suggest that biosignatures might be far more common than previously expected. Several additional worlds show atmospheric chemical ratios that suggest possible biological activity, though none yet display the unambiguous signatures found on K218b. The observation campaign has also revealed numerous worlds that appear sterile, despite being located in potentially habitable zones. These negative results are equally important for understanding the conditions that prevent life from developing or becoming detectable through atmospheric chemistry. International telescope time allocation committees are prioritizing biosignature searches over other astronomical research, recognizing that the detection of extraterrestrial life represents a historic scientific opportunity that justifies redirecting observational resources. The growing catalog of potentially inhabited worlds was beginning to provide enough data to answer one of science's most profound questions about our place in the cosmic order. The numbers that have haunted scientists for decades are suddenly rewriting themselves, transforming humanity from a cosmic accident into one member of a vast galactic community. The Drake equation, formulated in 1961, attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors like star formation rates, planetary occurrence, and the probability of life developing. For 60 years, scientists could only guess at most of these variables, leading to estimates that range from one civilization, us, to millions. K218b has provided the first reliable measurement of one crucial Drake equation factor, the fraction of potentially habitable planets that actually harbor life. If biosignatures are detectable on K218b after just a few hours of observation time, life might be far more common than the most optimistic previous estimates suggested. The discovery implies that hydrogen-rich ocean worlds represent a new category of habitable planet that wasn't included in previous versions of the Drake equation. These worlds appear to be more common than Earth-like planets and might actually be better suited for biological activity, dramatically increasing the number of potentially inhabited worlds in our galaxy. Statistical analysis of James Webb's early observations suggests that biosignatures might be detectable around 10 to 20% of potentially habitable exoplanets. This detection rate implies that life develops on most worlds where conditions permit, rather than requiring extremely rare circumstances or cosmic accidents. The 8 billion year time span available for biological evolution on K218b also affects Drake equation calculations about the development of technological civilizations. If life has such extended time periods to evolve complexity, the probability of developing intelligence and technology might be much higher than previous estimates assumed. Red dwarf stars, which host planets like K218b, make up approximately 75% of all stars in our galaxy. If these stellar systems commonly host habitable worlds with extended lifespans for biological evolution, The total number of potentially inhabited planets could reach into the billions. The new data suggests that our galaxy might contain millions of worlds with microbial life, thousands of planets with complex multicellular organisms, and potentially hundreds of technological civilizations that developed during the extended evolutionary timescales available around red dwarf stars. The Drake equation revision also has profound implications for the Fermi paradox, the apparent contradiction between high estimates for extraterrestrial civilization and humanity's failure to detect any evidence of alien technology. If life is as common as K218b suggests, the absence of detectable alien civilizations becomes even more puzzling. Possible explanations for the continued silence include the possibility that technological civilizations tend to develop communication methods beyond radio waves, that interstellar distances remain insurmountable barriers to contact, or that intelligence represents an extremely rare evolutionary outcome despite the abundance of simple life. The detection of widespread biological activity might actually increase the probability of eventually detecting technological civilizations, since James Webb's biosignature surveys are revealing target systems where SETI researchers should focus their searches for artificial signals. The cosmic loneliness that has defined human existence since the dawn of consciousness was giving way to the realization that we live in a universe teeming with life. Even if most of that life remains beyond our current ability to contact or visit, the implications of this discovery extended far beyond scientific equations and into the fundamental questions of human identity and purpose. The detection of life on K218b has shattered humanity's cosmic isolation and forced our species to confront the most profound questions about existence, purpose, and our responsibilities as members of a living universe. Religious institutions around the world are grappling with theological implications that challenge fundamental assumptions about creation, divine purpose, and humanity's special relationship with the cosmos. Some faith traditions find their beliefs enhanced by evidence of cosmic life, while others struggle to reconcile ancient teachings with the reality of alien biology. Educational systems are scrambling to update curricula that suddenly seem outdated and Earth-centric. Textbooks across every scientific discipline require revision to account for the new reality that life appears to be common rather than rare. Children who learn about K218b in elementary school will grow up with fundamentally different assumptions about humanity's place in the cosmos. International space agencies are redirecting budgets and research priorities toward astrobiology and interstellar exploration programs that seemed like science fiction just months ago. The detection of extraterrestrial life has created political pressure to increase funding for space science and develop technologies for eventual interstellar communication or travel. Philosophical debates about consciousness, intelligence, and the meaning of existence have taken on new urgency as humanity confronts the possibility that we share the universe with billions of other worlds harboring biological activity. Economic systems are beginning to factor interstellar perspectives into long-term planning and investment strategies. Industries related to space technology, scientific instrumentation, and interstellar communication are experiencing unprecedented growth as governments and private investors recognize the commercial potential of astrobiology research. Cultural movements are emerging around the concept of planetary stewardship and cosmic citizenship, arguing that humanity has moral obligations to protect Earth's biosphere as part of a larger community of living worlds. Environmental protection efforts have gained new momentum from the realization that planets capable of supporting life might be precious cosmic resources Legal scholars are developing frameworks for eventual contact scenarios, including protocols for information sharing, resource allocation, and decision-making authority when dealing with discoveries related to extraterrestrial life. International law is evolving to address questions that seemed purely theoretical until recently. Psychological research is investigating how knowledge of alien life affects human mental health, worldview development, and social behavior. Initial studies suggest that awareness of cosmic life tends to reduce anxiety about human loneliness, while increasing concerns about planetary responsibility and long-term survival. Scientific research priorities have shifted dramatically toward interdisciplinary programs that combine astronomy, biology, chemistry, and planetary science in ways that were previously considered too speculative for serious academic investment. Universities are creating new departments and degree programs focused specifically on astrobiology and interstellar research. The discovery has also sparked intense debates about resource allocation and research priorities. Some argue that confirming extraterrestrial life represents humanity's highest scientific priority, while others contend that solving terrestrial problems like climate change and poverty should take precedence over cosmic exploration. The transformation of human consciousness about our place in the universe was accelerating, but perhaps the most dramatic changes were occurring within the scientific community itself. Every astrobiology textbook published before the detection of dimethyl sulfide on K218b has become a historical artifact, rendered obsolete by observations that transformed speculation into established scientific fact. The discovery represents the transition from theoretical astrobiology to empirical astrobiology, the difference between wondering whether life exists elsewhere and actually studying alien biological processes through direct observation. For the first time in human history, astrobiologists have real data about extraterrestrial life rather than educated guesses based on terrestrial biology. University departments are completely restructuring astrobiology curricula to focus on comparative planetary biology rather than hypothetical biochemistry. Students now learn about confirmed examples of alien atmospheric chemistry alongside theoretical discussions of possible life forms, grounding astrobiology education in observational science rather than speculation. Research methodologies are shifting from laboratory simulations of possible alien biochemistry to observational analysis of actual alien biological processes. The field is developing new techniques for interpreting atmospheric biosignatures, modeling alien ecosystem dynamics, and predicting the evolutionary pathways that produce detectable biological activity. The confirmation of life on K218b has validated decades of theoretical work, while simultaneously revealing how much scientists didn't understand about biological processes in non-Earth environments. The hydrogen-rich atmospheric chemistry that supports life on this world was barely considered in previous astrobiology research. Professional scientific societies are establishing new journals, conferences, and research networks dedicated specifically to the study of confirmed extraterrestrial life rather than hypothetical biology. The International Astrobiology Society has tripled its membership since the K218b announcement. As researchers redirect their careers toward this rapidly expanding field, government funding agencies are increasing astrobiology budgets by orders of magnitude, recognizing that the field has transitioned from speculative research to a crucial scientific discipline with immediate practical applications. NASA's astrobiology program alone has received more funding in the past year than in the previous decade combined. The discovery has also revealed massive gaps in scientific understanding that require immediate research attention. Scientists realize they lack adequate theoretical frameworks for interpreting the complex atmospheric chemistry observed on K218b, leading to crash programs in exotic biochemistry and atmospheric modeling. In recent years, international teamwork in astrobiology has grown stronger. Scientists now realize that to truly understand the possibility of life beyond Earth, the effort has to be global. It is no longer about one country or one space agency competing with another. Instead, organizations like NASA, the European Space Agency, and many others around the world are working side by side. They are planning joint observation projects and sharing their research data in ways that were almost unthinkable just a decade ago. Another important development in the field is the growing focus on ethics. As researchers explore the idea of extraterrestrial life, they understand the responsibility that comes with it. New guidelines are being created to make sure that curiosity does not harm possible alien ecosystems. The protocols being developed are designed to reduce human interference and protect any fragile biological processes that might exist out there. Astrobiology itself has also gone through a major transformation. What was once seen as a small, specialized branch of science has now become a key discipline that brings together astronomy, biology, chemistry, geology, and atmospheric science. These fields are no longer working in isolation. They are now deeply connected. The study of planets like K218b, for example, requires knowledge and cooperation from dozens of different areas of science. But perhaps the biggest change of all is in how humanity views life beyond Earth. The idea of extraterrestrial life is no longer treated as mere speculation. It is becoming a recognized reality that guides the direction of scientific research and reshapes our understanding of life itself. Biology is now being seen not only as something tied to Earth, but as a phenomenon that exists across the universe. This discovery marks the beginning of a new chapter in human history. Textbooks are being updated as we speak, while scientists around the globe work tirelessly to understand the meaning of what has been found. What was once only imagination has turned into fact, pushing us into a new era where the study of life is no longer limited to our planet, but expanded to the cosmos itself.